That also then is the total variation data. It is also an estimate of the total amount of error. Okay. What else can I do to see if the terms go on forever? Okay. It's also the total deviation. You probably won't see this, but they will call it total deviation. That's what it is. You know, each of these scores deviates. So let's get an estimate of total deviation. Thank you, ma'am.
You're welcome.
And blank. Now, so the list goes on. Other terms that don't come to mind right away. All right. Now, why is that? Because of that formula. All right. And the list goes on.
Okay.
List goes on. And why? Because terminology trips us up. You know, terminology is like the language, right? And yet we use a lot of this different terminologies to say the same thing depending upon the specific analysis and whoever designed the analysis. So people that write language for a t-test will write what looks to be suspiciously an awful lot like what's going on in a correlation, but they might call it something different. So you have to try that out. Well, what is this really saying? It is simply saying this. This, we know that if scores didn't vary, if everybody in the world were 6 feet tall, nobody would be researching height because everybody's identical. The question would never surface. Why are we all 6 feet tall? Doesn't happen that way. The way it happens is, wait a minute, we got a guy out here who's 5 feet 11 inches. Well, wait a minute. That score varies. That person varies from this one. Now the question is, why? Why the variation? That becomes the research question. You see? I mean, if every student in the high school scored a 30 on the ACT, we would love it. But we wouldn't be researching student variation in ACT scores because everybody got the same score. But when it's not that way, we're out there looking at why did some kids score a 15, and why did some kids score a 33, and why do we explore that whole variation in between, right? That's the research we're doing. So in a sense, we are researching that. That's what research is all about, at least as far as we're concerned. Why does the variation exist? That's the baseline question. So, coming back here, all of this variation that's indicated by these terminologies has, let's see here. Has two components. Some of the variation in your data set might be related to socioeconomic status. Because we have SES in the data file, that's an effect. Okay? explore the effect of SES on test scores.
Okay.
We can explore till we're blue in the face, but we're never going to explain 100% of this, because there's always going to be unexplained. There's always going to be some component that's unexplained. Some of the variation we can't get a handle on. And so how do we help this process? Well, okay, I might have socioeconomic status, family income, right? But if I tack that with race as a variable, I've got two variables. Each variable will have some explained variation. And I put a third variable in there, and that'll have a little more explained variation. And a fourth variable, a little more explained variation. Each variable that I add in that has more explained variation takes up a greater and greater portion of this. And if you had such a thing as a perfect world, maybe you could find the 5 magic factors that would explain 100% of the variation. In that case, you'd have 100% prediction. You could predict total accuracy why a student, or what student would get what scores, because you explain all of the variation in its scores by those 5 factors. But if you look at chapter 2, when the author talks about modeling, whatever he puts in there, as far as this part of it, in the end, he's always got plus E.
Mm-hmm.
And that plus E is to always keep in mind that no matter how good we are at creating this model, in the end, there's always some of this. Does that work?
Mm-hmm.
No. That's not really intended to be a theoretical discussion, you see, because that becomes really the bottom line of what we're all about, is to begin to explain the variation through various variables on some output. And we analyze it, and hopefully we find that that new math program that we instituted last year, this year's kids, their average score jump so far, I can say that's not likely to be due to just random chance. Maybe, in fact, the program actually made a difference. Because I know, you just know, that if you didn't do anything, the math performance of last year's kids and the math performance of this year's kids would be different through random chance. Just random chance, just because there's a different mix of kids. The math program may have or may not have had any impact or a negative impact on their performance. But we're sorting that out, the effect, from the total amount of variation and trying to tease out the effect from the error. Or the math program from all of the other stuff that's out there that impacts how kids score. Okay. So this, to me, it looks a little theoretical. But I promise, if you go to chapter 1 and look at frequency distributions and z-scores and all of that, and then you put this on top of it, okay, and just carry it down through the outline and connect the terminologies to it, you begin to find a lot of redundancy in terminology, a lot of redundancy in application of the z-score, for instance, the z-table. And all around right now, the basic idea, can we sort out, and that's not very well worded, but the point being, it's always about the sample from the population. Okay? And in the end, you basically would say, that math program, in statistics talk, if the second year kids were statistically significantly higher, we would say they have now formed themselves into a different population of kids than were there last year. So the two populations of kids now become different, but the two populations are different by the analysis of them as a sample of the total population of kids. So This sample, which represents the population of the first group of kids, adequately says, this sample is different enough from this sample, which represents this hypothetical population, to say these two populations are in fact different. I.e., the math program made a difference. The math program won.
Okay.
Now that hasn't said whether the difference is important. It only says, is there a difference? And then the author also gives you a little discussion on effect size. And effect size then becomes only the question. Is the difference big enough to be important? You're sort of on the spot because you're right within the view of my but does that work? Does that work? Trying to connect the languages together, the terminologies together. And yesterday we looked at the normal curve, and then I didn't get into a lot of discussion on the z-score. I looked at the formula. It's mean subtracted from the score divided by the standard deviation. So the z-score is nothing but a standard deviation conversion. Converts everything to a standard deviation. And we know all of that intuitively based upon our, if you're 2 standard deviations above the mean, how are you doing in relation to the group that you're being compared to? Trick question. In round numbers, you're in the top 5% of kids.
Yeah.
Because the cut point is 1.96. But you're 2. So you're actually
That's 5%.
above the 95th percentile. And that is the value of the z-score. It doesn't matter what you're measuring. Once you make the conversion, you know immediately. You don't have to know that the average of this group is 6'2". If I say their z-score is 2, you know it's a rare population. They're definitely high. Okay, I'm gonna get this fixed and not a copy of this. Okay, why don't you guys get together and kind of look through the chapter, and whatever questions you've got, we'll see if we can tackle them. Okay.
Okay.
But the biggest one, probably the single biggest cost